So the topic is mathematics in the Vedic and Sutra age. So before coming to the mathematics proper, let us have a clear distinction regarding the source materials. As Professor Srinivas says that the Vedas are not texts in mathematics. So how do we know about mathematics in the Vedic time? The Vedic age was a period of great spiritual outpouring, and the Rigveda is essentially a mystic text. However, there is direct evidence of mathematical attainments in the Vedas, even in the Samhita and Brahmana literature, in two aspects. One is that how they express the numbers. They are not teaching you mathematics, but the way they are expressing numbers incidentally tells you something about the decimal genesis of the decimal system, and also that the seeds of algebraic mathematics in ancient India, even seeds of polynomials, you can see in the way they express numbers in the Vedas. So this is one direct evidence. The other is that there are examples of arithmetic operations during their mystic, even when they are describing some mystic phenomenon. So one can say that the keys to the roots of modern arithmetic, this modern arithmetic is not elaborated in the Vedas. These are elaborated in post-Vedic treatises. However, you can see the roots in the Vedas. So this is something which I'll come at the later part of my talk. However, there is also the indirect evidence, and this is easier. There are very elaborate descriptions of fire altars, Yagna Vedi, in Shatapatha Brahmana and even in the earlier Taittiriya Samhita. And these fire altars require sophisticated geometry. The sophisticated geometry is described slightly later in the Vedanga literature, but the applications are occurring in the Vedas. So therefore, there is an indirect evidence of geometric knowledge even in the Rigvedic period. So this is not direct, this is indirect. So there are the shapes of the Vedic fire altars are enormously complicated. Like you have this shape of falcon. The Vedas start with Agni Mile. Rigveda, the first line is Agni Mile. So when you are in a spiritual journey, you need aspiration. So that aspiration should really soar upwards towards heaven. So you need a picture of a bird which is really flying high. And the geometry is quite complicated. So there are other shapes. Now this is specifically directed in the Vedas that they have to be constructed with meticulous accuracy. And this quest for meticulous accuracy is at the origin of geometry, which is taught in school now. So this is what this is easier, I would think, because all of us have gone through the geometry, so you can identify with what I am saying. So now the mathematics in the Vedanga age, so that comes after Veda. So this is a period of transition from the mystic Vedic age to the intellectual classical age. So there the knowledge is given in the form of sutras, that's why the title Sutra. And the importance of mathematics is explicitly emphasized. This is very well known, so let me just skip it. Now in the Vedanga there are two texts which are very important for mathematics. One is the Sulva Sutras, which is part of the Kalpa Sutra by Bauddha and Manav, Apastamba and Kattayan. They are dated roughly 800 to 500 BC. And the Chandra Sutra of Pingalacharya, which is dated 300 BC. I don't know why it shouldn't be older, but let's not get into that. Now, the mathematics in the Sulva Sutras, there is of course explicit statement of what is known as Pythagoras Theorem, which is the pillar of Euclidean geometry. But what I would emphasize is this Pythagoras Theorem occurring in Sulva Sutras. It has been talked umpteen number of times, and it hides the more important issues. What they do with the Pythagoras Theorem, they do exact geometry construction. So by exact, what I mean is that you remember why geometry was thought to be so formidable in school. You are allowed to use only unmarked ruler, that is you can't measure, and compasses. See, for example, if you have to bisect 10 centimeter, it is not I mean, you will not be allowed to put your dot on the 5 centimeter and say, I have bisected it. You have to take a compass and you have to do certain things. And that is what makes geometry so formidable. Now, that sort of construction you find in the Sulva Sutras. And this is something which gets lost in the din about Pythagoras theorem and its proof. And this sophistication, this exact construction shows an enormous amount of sophistication. It shows a blend of geometric and algebraic insights and skill. Now, algebra is not just x, y, z. See, these x, y, z are symbols to express certain algebraic truths. Those algebraic principles can be stated even without x, y, z. If you state it in words, that's also algebra. And these algebraic principles, they are stated in a geometric form in Sulva Sutras. For instance, so you don't have these equations, you don't have these identities, but these identities are expressed geometrically. So I'll quickly show some diagrams which would. So first of all, the Bauddha and the Pythagoras theorem occurs in Bauddha and Sulva Sutra and all other Sulva Sutras. And Bauddha and Sulva Sutra is the oldest literature, available literature, which makes an explicit statement of the Pythagoras theorem, though it was known much earlier than Bauddha, and not only in India, in other countries too. The one difference is Pythagoras theorem, as we know it from Euclid and what we are taught in school, is a statement about right angle triangle, and here it is a statement about the diagonal of a rectangle. So the diagonal of a rectangle produces an area which is same as the sum of the areas produced by the length and breadth respectively. Now you see the sophistication of the Sulva geometry. Construct a square which is n times a given square. So suppose the given square is of length a. So your square will be of area ns square, which means you have to construct square root of n times a. So essentially construction of square root of n. Now these are problems which are also done in Babylonia, but what Babylonians will do, let us say you have 10. They will just take square root of 10. That is measurement, which is not allowed in our school, because measurement inevitably involves inaccuracy. And Vedic mathematics has to be absolutely accurate. So look at their construction. So they tell you, take n minus 1. So look at the base. Base is formed by n minus 1 copies of your given A, and you also form n plus 1 A copies and bisect. So you form this isosceles triangle. The two sides are n plus 1 A by 2 and n plus 1 A by 2, and the base is n minus 1, and then you bisect it. Then that altitude gives you the answer. So this is what is given in Katta and Sulva Sutra. Now you note one thing, that it gives you exact construction of root n, no measurement or approximation. So this is where the sophistication lies. And it's not moving fast. Something is going wrong. So apart from this one. Okay. So apart from so it's an application of Pythagoras theorem. You see the identity ns square
You can use the pointer, sir.
Yeah. Oh, I didn't notice this. So you can see this identity. N square equal to n plus 1 a by whole 2 square n minus 1. Now this is something which is, this algebraic principle is stated in the geometric form. It is a geometric demonstration of the algebraic result. And here, this is now a question of appreciation of So what will be said is that you see that in Vedic time there was no algebra. Whereas you see an algebraic principles. Now what is the conclusion you draw? That they were inventing mathematics which is algebraic in spirit and substance, though not in form. But the fact that they did mathematics which is algebraic in spirit and substance much before the genesis of formal algebra makes them much greater as algebraists. This is something, a very important point in mathematics appreciation. See, when Manjul Bhargav got this, his composition laws, he was talking about Gauss. That Gauss gave group theoretic laws before the invention of groups, and that makes his laws more remarkable. So this is something which has to be learned regarding mathematics appreciation. That they did algebra, which was they did mathematics. Well, let's avoid the word algebra. They did mathematics, which is algebraic in spirit and substance, before the genesis of formal algebra. This makes them much greater as algebraists. And similarly, you have the construction. This goes back to Baudhayana. Square equal in area to a rectangle, which is construction of root AB. So this is the rectangle, given rectangle. This is side A, this is side AB, this is A, this is B. So what they say is complete the square B. What remains is A minus B, bisect it. So this part is A minus B by 2, which means this whole thing is A plus B by 2. Now they say that draw an arc. So which means that and meet it in this side extended. So it meets here. So what you get? This is this part is A minus B by 2, this part is A plus B by 2, and they say that take this. So what do you get? It is an algebraic demonstration of the identity A plus B by 2 whole square minus A minus B by 2 whole square equal to AB. Just see the sophistication. And A. Seidenberg says that the elements, this is entirely in the spirit of the elements of Euclid. I would say, that is Seidenberg says, it is more in the spirit of Euclid than Euclid himself. He said it in the origin of, it's a very important paper which is suppressed naturally, the origin of mathematics in 1978. So you see again the exact construction of root AB and the geometric formulation of this. Now the contentious issue that whether proof occurs in the Sulva Sutras, proof of the Pythagoras Theorem. Of course, they don't say, here is the proof. Because you have to note the distinction between Euclid's elements, that's a textbook in pure geometry, whereas Sulva Sutras are actually engineering manuals. It's not announcement of discoveries, so there is no need to justify the results. It is like you look at a modern textbooks, it doesn't give elaborations about why Newton's laws of motions, what are the experimental verification of Newton's laws of motion or Newton's. They just tell you these are the laws and then come quickly to the principles where they are applied. That is the role of the Sulva Sutras. So the purpose is that Vedic fire rituals, and this knowledge is much more ancient. However, the question is whether they knew the proof. Now you see that in Baudhayan he states the theorem in Sutra 1.48. In 1.49 he gives some examples of integers which satisfy this, what are called Pythagorean triplets, and then immediately after that he gives a construction. This construction is how to draw a square equal in area to two given squares. So this is the construction, this is the given square, one given square, and this is another given square. And the final square which comes out is this. So why what they are saying is true is this. What is happening is that originally you have this much area. There you are cutting out this triangle and replacing it by this triangle, and you are cutting out this triangle and replacing it by this triangle. Now they may not be saying that side angle, side congruency, these are just words. But the spirit is there, that this triangle and this triangle, they are congruent. And so why they are congruent, that those finer things, that's a matter of setting up rules. That you don't see there. Now, doesn't it give you a demonstration of Pythagoras theorem? Because you see, look at this rectangle. Look at this diagonal. This is a square on the diagonal. And this square is same as the square on this, which was the original thing, and the square on this, which is same as square on this. So this is a demonstration of Pythagoras theorem. So those who are giving you this construction, they of course know that why the theorem holds. It's not empirical knowledge. Now this has to be very clearly understood. Now, there are other things, just because I'm giving too much emphasis on geometry, there are examples of operations with fractions and implicit use of surds. And also rational approximations. So there are numbers which cannot be expressed as rational numbers, but they are giving good rational approximations. And also there are, so not always that you can make such ruler and compass type constructions. For example, converting a circle into square and square into a circle, that cannot be done accurately. I mean in those methods. So there they are giving you approximate methods too. So now I come to a bit of historiography. So first is, let me start with the positive things. That those who have done research on Sulva Sutras, the kind of appreciation they have made, and also we should remember some pioneers. So at 3 levels, one is Thibau. He really brought out the Sulva Sutras into the English scholarship in 1875. Vibhutibhushan Dutta, whom Professor Srinivas mentioned. I mean, whatever we know about ancient Indian mathematics, I think 95% of that is due to Vibhutibhushan Dutta, which is, 100 years and anyway. So that shows us that in 1932, Vibhutibhushan Dutta and Seidenberg, whom I was quoting, he is a very important professional mathematician. So this professional mathematician's view on this, that you get in Seidenberg. So all 3 are pioneers in 3 different ways. Now you look at the moving tribute of Vibhutibhushan Datta. How great is the science which revealed itself in the Sulva, and how meager is my intellect. I have aspired to cross the unconquerable ocean in a mere raft. However, so let me skip this. However, the Sulva Sutras were undermined after Thibau made his discovery. So I don't have time to get into the entire history. What I'll do is I'll summarize Seidenberg's summary of what was going on. Just see. He didn't, meaning Thibau, did not formulate the obvious conclusion, namely that the Greeks were not the inventors of plane geometry, rather it was the Indians. This is the picture. In 1875, it was thought that the Greeks invented plane geometry, but Thibauts' findings seem to be violating that. And though Thibau didn't say it explicitly, that is the message the Greek scholars saw in Thibauts' paper, and they didn't like it. And now remember Seidenberg's expression, if the Indians invented plane geometry, what was to become of Greek genius or of the Greek miracle? Most of the refutations were mere haughty dismissals. Anyway, the damage had been done, and the Sulva Sutras have never taken the position in the history of mathematics that they deserve. Now, this comment by Seidenberg should be well known. Now, what I have observed is that this tradition, mark the phrase haughty dismissals. I would say that in Europe, this kind of tradition of haughty dismissal is not so conspicuous now, but that tradition has been taken over by a large section of Indian intellectuals, and paradoxically after India's independence. I am not a historian to go into the causes of that. Now, there is of course this extreme about the outright denial of ancient Indian mathematics. And you keep on hearing umpteen times that there are 2 people, one claiming that there is everything and the other claiming that there was nothing and there has to be. Now, what I am really alarmed is this middle of the road approach, this moderation, the striking of balanced views. And balanced view means compromise. Okay, I give you this, you give me that. I give you Aryabhatta, Aryabhatta was great, Brahmagupta was great, but there was nothing. So it is a trade-off. So what I am worried about is this balanced approach to ancient Indian history, which I find is more pernicious than there was nothing. Now I think nobody believes, but balanced views are very believable. So what I'll do is that analyze the different phenomena of balance. Two examples. One is that the patronizing praise for post-Vedic greats like Aryabhatta and Brahmagupta has to be balanced by denial of mathematics in the Vedic era. And there is this thing, and also this history has become very axiomatic. Like in mathematics, we have axioms that parallel lines do not meet, etc. That gives you this. So history is axiomatic. So one axiom is that post-Vedic flourish is due to foreign traditions like Babylonia, etc., and Buddhist skepticism. So anyone who traces the origin of Indian mathematics to Vedic era has to be a partisan. Now, this is one thing. The other is that so the balances is not very uniform. Another balancing is that they do accept statements in Vedic era that there has been mathematics in the Vedic time. So this acceptance is balanced, like statement of Pythagoras is there in the Sulva Sutras, has to be balanced by denial of some aspects, like the aversion of proofs, and suppression of the other aspects, like the sophistication of the geometric constructions. And also you have to distinguish that there are various factors in these misrepresentations and omissions. I mean, don't club everything in. There is partly ignorance and partly dishonesty. Sometimes it's a combination.
Mostly dishonest.
Okay. And failure to appreciate, that is also another thing which many people fall in that trap. Failure to appreciate mathematical subtleties. Now, I'll not give examples of, people who are out and out in that extreme this thing. So I'll give you examples of balanced views. And I'll give you examples from people, because that I find is more dangerous, of people who are really great achievers, who have done the country proud, and very clearly they love the country too. That comes out from their various activities. I mean, some of their activities may be misguided, but they really love the country. I mean, very nice people. So one is Amartya Sen. So you look at the Argumentative Indian. Now, I mean, let us not say, try to conclude that just analyze the statements. You see, as it happens, despite the richness of the Vedas, so you see this balancing, because he has to deny the mathematics, so it will be balanced by a statement of richness of the Vedas in many other respects. There is no sophisticated mathematics in them. Now, you see the difficulty that many people will agree, because you see the Vedas are not giving, of course, Vedas are not statements of mathematics. However, you see that it's not, so there are two things here. One is that Vedas indirectly are giving you that much mathematics was known in that era. But you see the Sulva Sutras are also left out, because there was, however, much of both in India in the first millennium CE. So by now it is clear that Sulva Sutras are in BC. So Sulva Sutras are out. These contributions were, that means first millennium CE, so this Aryabhatta Brahmagupta. So their contributions were early enough in the history of mathematics and science to demand respectful attention. So the solid Aryabhatta Brahmagupta, they are, so then why do you go, and he mentions BJP created proposed state books with little reason and even less evidence to place the origin of some of these contributions to the much earlier Vedic period. And then he goes on that three distinct errors, and some of the other errors were, I suppose, discussed yesterday. The manifestly false affirmation that Vedas contain much sophisticated mathematics. Actually, Vedas, I mean, they can give you they show you that the decimal system was known in the oral form. So that is indirectly sophisticated mathematics, and the other is they are giving you constructions which are they are giving the applications of geometric constants, and those geometric constants are sophisticated. So there are these fine shades. The non-partisan readers cannot find them there. Now, Are you not reminded of Seidenberg's phrase, Hotty Dismissal? Because, and this really rhymes with what the Vedas argue, because if there is mathematics in the Vedas, what happens to the Greek miracle? Now, if there is mathematics in the Vedas, what happens to the Buddhist miracle? This Buddha bringing in rationality and supplemented by knowledge coming from Greece and Babylonia and Rome. And you contrast it with Vibhutibhushan Datta's touching tribute. Now you see that sometimes even the logic, when you discuss ancient Indian mathematics, probably the logic is not even needed. The third claim, by the way, also has the effect of implicitly asserting that Aryabhatta or Brahmagupta or Varahamihira were not original in the 5th to 7th centuries. Now the same intellectual is mentioning, we learned a lot about in a different gathering. We learned a lot about theorems, proofs and rigorous mathematical reasoning from Greeks and Romans and Babylonians. Incidentally, Romans did not have any contribution to mathematics. So forget about theorems, proofs and rigorous mathematical reasoning, and as somebody pointed out, one contribution is killing of Archimedes. Anyway, so there is no shame in learning from others. So if you put two together, my conclusion is there is no shame in learning from Greeks, Babylon. The only shame is learning from the Vedic tradition. So that undermines Aryabhatta and Brahmagupta if he is following the Vedic tradition, but if he is following, then there is no shame. And Indian Science Congress, he says that those looking for origin of mathematics in the Vedas would be completely barking up the wrong tree. And so let us see who are the people who have been barking up the wrong tree. So I'll give you one example. Swami Vivekananda had said, when the germ of every Aryan science is found in the Vedas and every step of any of those sciences can be traced with exactness from the Vedic to the present day, what is the necessity of forcing the far-fetched suggestion of the Greek influence of them? And you can see that how Swami Vivekananda's summary matches with this influence in mathematics. Now, let very quickly give you another example of balanced presentation. Jayant Narlikar, another great achiever and has done so much for promoting astronomy and astrophysics in India. The Shulva Sutras contain Pythagoras Theorem, but not the proof of the theorem. And just a few days back, I heard this being quoted in a seminar at Ramakrishna Mission by a Ramakrishna monk. And he says, nevertheless, as a correct result, the statement should be renamed as a Shulva theorem. So he is giving so much. Therefore, his statement that there is no proof is highly authentic. Contrast this with what the mathematician Seidenberg says. Many writers say that there are no proofs there. We can only suppose that these writers have not bothered to examine the work. And Manjul Bhargav, in a personal correspondence with me, you see that proof, sometimes you may say that proof means that it should be in a logical axiomatic framework. Manjul Bhargav used a fantastic phrase in a personal, that then it is pretty clear that the Shulva authors knew why the theorem is true. So that is the phrase, why the theorem is true. So, Shulva Sutras are meant to be engineering manuals, and they are offshoots of a much older Vedic tradition which had savants who had not only realized some of the fundamental principles of plane geometry, but knew why they worked and how they yield accurate constructions. Now here there is another point which I would like to mention, which gets lost, that the original creators of a discipline provide the insights and the essence of a discipline. And the neat edifice which you see in, for example, in Panini in India or Euclid, that emerges later. This is true in, I'll give you an example, that there is a subject called algebraic topology. And the founder it is attributed to Poincaré. He is universally revered as a founder of topology, algebraic topology, because he gave the deep insights and essential ideas. But this Euclidean or Paninian arrangement, that comes 50 years after it. And those who did that, Eilenberg, they are not regarded at the same level as Poincaré. Now, what Dieudonné says about Poincaré, just match it with the Vedic thing. We should not look for precise definitions in Poincaré. It is often necessary to guess what he had in mind by interpreting the context. For many results, he simply gave no proof at all. This is the story about late 19th century. So nobody says that Poincaré's knowledge is empirical. So this is something which you have to realize. Now, I quickly get into something which is much more sophisticated about the decimal system in the Vedas. This is very subtle. So, decimal number vocabulary goes back to the Rigveda. Rigveda already has single word terms. So this is something important. Like 10,000 is not a single word. 100,000 is not a single word. So they are giving you single word terms for the 9 primary numbers, 9 multiples of 10 and first 4 powers of 10. And numbers are named by combining the above terms, the way we do it now. And that is there in the Rigveda. And numbers are represented in decimal system in the Rigveda, in all other Vedic treatises, and in all subsequent Indian texts. No other base occurs, except a few instances of base 100. Now the point is, and then there is just after the Rigveda, in Yajur Veda, there are these high powers of 10. What you note is that the words are single word terms. So that is sowing the seeds of the place value notation. Specific one word term for each power of 10 up to 10 to the power 12. And you see the verse, each term is perceived, practically defined to be 10 times the preceding term. Now, so there are various things to it. One thing is that our decimal notation, so point I'm trying to say is that this zero and decimal notation has hijacked the mathematical importance of the decimal number vocabulary. Okay? You see the digits, they correspond to word numerals and place value corresponds to the powers of 10. So powers, names for powers of 10, they had sown the seeds of decimal. And one person who has been arguing on this is Professor Divakaran. He is the only person who I know has been emphasizing this point. Let us take the number 2108. How you obtain this 2108 from this Vedic thing? 3 principles say that suppress place names for powers of 10s. Like orally you say 2108, suppress the words 1000 and 100. And replace word numerals like 2 and 1 and 8 by symbols. So this idea is needed. Replace 2 by a symbol, 1 by a symbol, 8 by a symbol. Suppress these words 1000, 100 and use a 0 symbol. That's a new idea which will be needed. So what I'm trying to say is this is decimal notation. This has been talked about umpteen number of times. But this has sown the seeds for this. That is not emphasized. And this is Vedic. Vedic means actual Rigvedic. Now, this is much more subtle than that. So one thing is that the key to decimal place value notation lies in Vedic Sanskrit number vocabulary. And this is a statement which you rarely find in history of science. I got it in Swami Vivekananda. The 10 numerals, the very cornerstone of all present civilization, were discovered in India and are in reality Sanskrit words. And I was trying to understand what is said here. I was taken aback. And what I'm saying you is my effort to understand what Swami Vivekananda has written here. Now, there is still something more subtle than that. That algebra is about polynomials. Polynomial and algebra, modern algebra, these are interchangeable. And there's in 20th century, there was a very great mathematician from India, who was one of the really top mathematicians, Abhyankar. He has a poem, Polynomials and Power Series, May They Forever Rule the World. It starts with this. Now, you look at this polynomial aspect of the decimal system, and what I mean is that really the oral thing, not only the written. So, polynomial can be written in 2 ways, like ax squared plus bx plus c. In general, you can write it in this way. But what you see also in books is that you can also suppress x and write it like this. Does it not resemble the decimal system? So, example is 2x cubed plus x squared plus 8. This is the standard way of writing polynomials. But polynomial can also be written and is written in some books as 2108. But this is not so common. And just compare. Number can be expressed in decimal system in 2 ways. The one is the Vedic number vocabulary. 2108, and this 2108. It just matches this. So what is said is, and this is moving too slowly. This, yeah,
Go up, sir.
yeah, that.
Below. You want up?
No, up, yeah.
Up.
So you see this dasa corresponds to x, shata corresponds to x square and shastra. Of course, you may say, as Professor Divakaran says, that there should have been a word for power of, dasha square. But you see, that makes it messy. So because it is not that they are trying to impress you with this. So they have this idea that it is power, but for expressing word, a single word would be more convenient. So you don't have dasha square, you have a word, separate word shata and separate word shastra, but the principle is unmistakable. Now, whatever I'm saying is that is it an afterthought that having got these polynomials, now we're attributing decimal. Now I'll just show you when did polynomials appear in Europe, 17th century, and who is associated with polynomials and power series? Newton. So this inspiration for algebra of polynomials. So Newton says in 17th century, since the operation of computing in numbers and with variables are closely similar, I am amazed that it has occurred to no one to fit the doctrine recently established for decimal numbers. You see, this decimal system was standardized just before Newton in similar fashion to variables. Now there is and especially since the ways, so this doctrine in species means this x square, x cube, has the same relation to algebra that the doctrine in decimal numbers has to arithmetic. So this algebra of polynomials is inspired by the decimal system, and you can clearly see the decimal feature is this polynomial feature is there in the oral vocabulary of the, which is there, goes back in the Rigveda. And to the best of my knowledge, Newton did not belong to BJP, right? Okay. And then there are other people who have been, so Newton is explicitly acknowledging this. And then you look at the other ideas which are coming out. Binary expansion, which is at the heart of the computer, comes up just after decimal is introduced. Periodic expansion in Hensel. Abhyankar in 20th century tells you, in his own research, decimal is inspiring even 20th century research, that he has some geodetic expansion, which is a generalization of the idea of decimal expansion. Let me go over to, so there are, various impact, like the basis of the modern methods of fundamental operations. If you just think about it, they are all based on the decimal system. The seeds of algebra, and in India, Brahmagupta gave polynomials 1,000 years before Newton, because Brahmagupta grew up in the decimal system. And this helps Indian astronomers to express things in large numbers, and then mathematicians to deal with problems involving large integers, as you can see the examples, early anticipation of infinity. And there are various subtle mathematical things which are the outcome of decimal things. And so do we not owe a debt of gratitude to the ancients? Then I just quickly go over this. Shatapatha Brahmana gives you several factors, all the factors of 720. So how you know that division was known? All the factors of 720 are displayed in a long passage. See, he divides, Prajapati is dividing his body into two. There were 360 bricks. Then he made 3 bodies. Then you see 380. So like that it goes on, and all the factors are given. So this is the direct evidence that division was known. How they did it is not known, but division is there in Shatapatha Brahmana, which is out and out Veda. Then there are phrases like 1000 is divided into 3, then there is a remainder 1. And Shatapatha Brahman also gives a sum of an arithmetic progression. So why suddenly AP? See, they are telling you about gifts, the number of sacrificial gifts. In that context, these numbers are coming up. So this 3 into this thing. So this things, you see that. Now there is also this Chanda Sutra quickly, I'll just go through it, that they're binaries to decimal. So they are, in Pingalacharya, in Sanskrit there is Laghu and Guru, two kinds of meters. So he gives you a system of coding of each meter with a number. And conversely, given a number, how to get back to the meter. So I'm not getting into the mathematical details, but that is exactly the conversion of the binary number to decimal and the decimal to binary. And then he gives a very remarkable algorithm for quick computation of 2 to the power n. So that would take something like 5 minutes, so I'm omitting it. And then there is a version of what is known as a Pascal's triangle, which is a very important combinatorial principle. And what is most important is that the strong tradition of combinatorial mathematics in India, which Professor Srinivas and others have brought out in much details, is inspired by Pingalacharya. Again, this is not an afterthought. The Pingala is mentioned in those texts. I mean, unfortunately, contradicting, this Greek miracle and Babylonian miracle and Buddhist miracle. So here I had included a quotation from Sri Aurobindo, which says that these early wise men, so in the Vedic time, whether there were mathematicians or not, they were not scientists, they were mystics. But the point is that what I'm trying to say is that this mathematics might have come from mystics, not professional mathematicians. It's something like physicists giving mathematics. That doesn't become that you don't have to belong to a department of mathematics to come up with a discovery which will be called mathematics. So physicists may give. So mystics might have done it. So the science of mathematics or discipline of mathematics might not have been there in the Rigvedic time. That is possible. Oh my God. What is happening? So there are these references, and just to tell you that how many people had become partisan both in India and abroad, because those who see mathematics in the Vedic time are partition. That's an axiom. So as a corollary, you see that the titles in the red colored titles, Science of the Sulva, in B. Dutta has an article, Vedic Mathematics, Seidenberg has article, Ritual Origin of Geometry, Origin of Mathematics, etc., Geometry of Vedic. So there are many references for geometry. Yeah. So just keep on looking at it. And S.G. Dani has an article, Geometry in the Sulva Sutras, and there he has used the word sophisticated, which would again mean that he is partisan by axiom of Amartya Sen. I mean, partisan of the BJP RSS type. Anyway, finally, that blue one. So one last page. No, it's just a little up.
Up, sir?
It's slightly up.
You want to go up, sir, or down?
No, just the first line is missing here.
Just go up one line. Good.
So, sometime in 1911, Sri Aurobindo had written, "A time must come when the Indian mind will cease to think or hold opinions at second and third hand." So and now there is a very ominous phrase in Thoughts and Aphorisms of Sri Aurobindo. He says, "Break the molds of the past." About that, there is absolute unanimity. Though intellectuals sometimes tolerate this, break the molds of the past, but keep safe its genius and its spirit. And what I observe is that even if there is some tolerance of this maintaining molds of the past, okay, rituals jo hai rane do, this moment you bring in genius and its spirit, people almost take offense. But if you don't keep safe its genius and its spirit, what Sri Aurobindo says, or else thou hast no future. Okay. Thank you. I think
we have time for just one or two brief questions.
Then we can bring this across.
Actually, since I am in a research institute and not directly involved in mathematics. So mathematics education, I would make a distinction between two aspects. One is to try to motivate people or make people understand mathematics. That's an important area. The other is that, let us say, somebody who is into mathematics, who loves mathematics and is good at it, to really bring him to the top. Now, regarding the second thing, I can share some insights because, since I am in the researcher. So, one important aspect of history of mathematics, and this is not my statement alone, this has been stated by Leibniz, by Andrevel, etc., is that the art of discovery should be promoted. Now, this is, of course, may not be applicable to every child, because not all child will become research mathematicians, but those who will be in a somewhat mathematical discipline, the art of discovery can be promoted. And there the history can, particularly the history of Indian mathematics, has a very important role in two ways. One thing is that let us look at this decimal idea. The fact that polynomials are embedded in the decimal, this helps in understanding mathematics better. So like Abhyankar is getting his own idea because he is a thinker, not just a doer. Thinker come doer. And also that people are told that Newton is great, but you try to show his greatness that, okay, here is a decimal thing. So there are two things about it, that the decimal system, the Vedic decimal system is so great that it has been inspiring, giving inspiration. So that is one thing. And the other is that not everyone is capable of bringing out what is dormant in the decimal. This is Newton's greatness, that he brought out the polynomials out of the decimal system. This has to be told. Or Brahmagupta brought it out, and Leibniz has been bringing out the binary expansion. This would promote creativity. Second thing about the Indian mathematics is that Indian mathematics was done much earlier than the corresponding things when it came to Europe. Now that is very important for promoting creativity. I'll give you one example of Brahmagupta. So he did fantastic, gave composition laws which came in Europe in 18th century. Now Brahmagupta's mathematical background is not much different from what students know now. So here you can show them an example of abstract mathematics without much of baggage, much of formalism, because that formalism is not there. So they can directly go to the point. Whereas, let us say you look at Brahmagupta comes up again in Euler. But you see that Euler has great predecessors, Newton and Fermat, and so many people have gone beyond it. A student, he doesn't understand how Euler, because Euler thing is coming as part of a heavy machinery. So the student's creativity, what you can do is that you can transmit him knowledge, and knowledge is of course very important, but the creativity aspect will not come. Whereas when you show it through Brahmagupta, the creativity would be promoted, because that comes at a very early stage. A student can identify with Brahmagupta does, because Brahmagupta's only predecessor is Aryabhatta. By now, most school students know what Aryabhatta knew as far as mathematics is concerned, except for one thing, then that can be taught to them, some Kutaka algorithm that can be taught, and then Brahmagupta comes up. And this is something, this facility you don't have with Western development except Euclid. I'm not really, but the more recent developments, that is something huge. So that has to be packaged as knowledge. It can't be given in the form of creative development, because you don't just have time for it. So you go fast, and then later you can get into history. Like Galois, it is impossible to understand what really Galois did, because nobody in Galois' time understood him. So the modern simplified version is taught, and then it is good to go back to Galois. Whereas Brahmagupta's thing is that right now you can teach not every student but the bright students what he did. And this Vedic thing, Pingalacharya can definitely be given to all school students, how he computed 2 to the power n. This will promote creativity, binary decimal.
Thank you, Professor.